So this is something called Automation Studio, and it's a neat little program that I can use to give you an idea of what's going on with these logic gates. So learning task 2 starts off after you do the numbering system, of course. The basic or common logic gates, and they are AND, OR, NOT. The NOT is also called an inverter gate, and something called a NAND, which is the inverse of an AND, and a NOR, which is the inverse of a NOR. So they are basically little chips. They got more than, as you can see here, I've got an A and a B, but on the chip itself there's about 10 pins. And in this case, this switch is set up to indicate a 1 or a 0, and the 1 would be voltage, 5 volts or whatever, depending on the chip and the specs for the chip. So there's a power and a ground point on. I'll see if I can find a picture of a chip just to give you an idea. So the AND instruction is kind of like two switches in series. So if I click on this switch here, you can see that it changes color. So now we are passing voltage into the AND chip here, but we don't have an output yet. So we have a little logic probe on the output that is indicating whether we have a high or low. And right now it's still low. Our LED light is dark, so it's black, so our light is on. And when I hit the other switch, it changes state. So we're actually turning our light on. Now this is a diode, so we're going to think of electron flowing this way. So I know it's kind of messy. Sometimes electronics is a little easier to understand if you follow electron flow versus conventional flow or vice versa. Now I notice over here something called a truth table. And this is set up to get the right combinations. In this case, we have 4 combinations, all off. We don't have an output. B on, so we can simulate that by turning A off. B is on, which is a count of 1. We don't have a Y out, it's not on. We can change that over to just A on, and we still don't have an out. But if we put A and B on, we do. So here's an example of it being as switches. So we can see here like 2 switches in series. And then it finally comes on. So we need A and B to get our output Y. So it's like 2 switches in series. The other instruction is called an OR. And looking at the truth table here, you can see that an OR instruction has, in this case, 2 input OR has the same amount of combinations, but we've got, I can scroll up a little more here just to get the switches. It's like 2 switches in parallel. So think of start buttons. So if I turn B on, we can see our light turns on, which our truth table here says, yeah, it's true. If I turn B off and turn A on, yes, that's also true. And of course, the one here indicating we're giving it voltage. And of course, I've turned them both on, which we have here. Well, it was already on. We really can't turn it more on. And there is our equivalent of switches in parallel. And if they're both on, of course, we can't turn them any more on. So it's either one makes the other redundant. Something called a NOT, or an inverter gate. The module talks about the NOT like a switch bypassing a light. So I've kind of shown it here as a normally closed switch. Later on, you'll see that it can be indicated that way as well. But usually there's something turning a coil on. This way we'll still get the same results. So right now we have voltage coming from the source. So just this little circle here means there's a 1 there. So that means there's voltage there. So it's the opposite, it's the inverse. So if there's a 0 here on the input, the output here is true. We have voltage or a path for voltage. So here's our light, it's on, right? We have a 1 there. And so bar A is the opposite of A. So inverse of A is going to be the opposite. Now, if I give the gate a voltage, the light goes out. So here now we are bypassing this voltage to ground. You can't see that within the little instruction here, but once again, these have 10 pins on them, these little chips, and there's a lot more going on than what we see here. The basics of it, though, is a high input means a low output, and a low input means a high output, which is like a switch down here, normally closed, where we have the light on. If we open it, we take the voltage away. So here we're sinking our voltage away, the light goes out. Here the voltage can basically come from this direction, if we can imagine it, or this way, back to our source on a different pin. A little funky, but yep, that's how they kind of work. It's an inverter gate. Now, something that is opposite of an AND is a NAND. Now, I don't have the switch equivalent here because I don't. I was trying to mess around with it to get it to work, but it's a little different. Your module shows a pretty good example of a NAND bypassing power to a switch through a current limiting resistor. Otherwise, we'd have a short. But you'll notice that the truth table for the NAND is the opposite of an AND. So that little circle in the front here is like putting the inverter gate, this guy, in front of the AND. See, this AND gate doesn't have the little circle, so it's not, the output is not inverted. So with the NAND, it's like having an inverter gate put on an AND, and we have an inverted output. So what does that mean? That means if we don't have an input, or in other words, zeros on the input here, that means we have power, or we have a 1, or a path for the power to flow. And you can see with a logic probe that that is true. And when you look at the truth table, the light is going to stay on until we have 2 highs. So with an AND, 2 highs cause the light to come on. In this case, it's the opposite. 2 highs cause the light to go off. Okay, so if we turn this on, nothing happens yet. Turn this, oh, it's still on. So this one is broken. Let's see if I can refresh that. So that I know I had a bit of troubles with this simulation every now and then. We'll stop it and try again. There we go. Our light is off now. So good. So the NAND, it's almost like the NAND. Okay, the light is off right now. Yeah, there we go. So 2 highs, 2 1s on the input, which is indicated down here as 2 highs, give us a 0 light. Whereas any one of those turns the light on. Right, so in this case, we have 2 zeros on the input, indicated by here. Our light is still on. If we turn B high, which is indicated here, our light is still on. If we turn A high, it's still on. So we need 2 high to get our output low. So it's the exact opposite of an AND gate. It's called a NAND, or not AND. The opposite of a NOR, or I should say, is a NOR. So as you can see here, the truth table for the NOR is the opposite of an OR. So in this case, 1s make our output 0. Right now we can see that we have a 1, which means we have voltage, we have a path for voltage, to control this light. If I could do B first, so B makes a 0. And A makes a 0. And of course, 2 highs make a 0, just like, or the opposite of an OR, where 2 highs make a high or 1 high makes a high. So those are the basic instructions. There's one other that's a little different, called an XOR, and I don't have a simulation for that offhand. I don't think I do. I'll have to check for one. I know I've got something maybe built that looks a little different, but it should work. The only difference between an XOR and a OR is on the XOR, 2 highs here would actually make a low. So it's kind of like the equivalent of a 3-way switch. Okay, so make this bigger. I wonder if that'd be better. Maybe that would be better. Sure it would. Okay, so kind of looking back to that again. There's our AND gate. 2 highs make a high. And there's our truth table that proves it. And our OR gate, either high makes a high, or both highs make a high. And the equivalent of a switch, switches in parallel versus switches in series. So an AND is like switches in series, an OR is like switches in parallel. Back down to the inverter gate. High makes the output low. The low makes the output high. It's like a normally closed switch, or a switch bypassing the load. And the NAND is the opposite of an AND. A little circle on the output says it's like having an inverter gate on the output of an AND. And in this case, it's the opposite. So if the light is on, we need 2 ones to make a 0. So in this case, highs make zeros, where in a NAND, or I should say AND, highs make a 1. For the NOR, highs make zeros, versus the OR, highs on the input make highs on the output. And of course, the exclusive OR is, the only thing that's different is we have 2 highs up here make the output low. That's the end. Let's go back down. There we go. 2 highs here make the output low. And there's one other, if it's in the module or not. An exclusive NOR. That might come up later, but it's just one of those things that the book sometimes talks about, sometimes doesn't. Now, each of these guys have what we call a Boolean expression. Okay, let's see if I can go back. Okay. I'm going to recap once again with the module pictures. Let's take over this screen. Share my screen. And we want to be on learning task 2. So there's our AND symbol again. And once again, it's the equivalent of 2 switches in series. They've just done it a little differently in this case. The Boolean expression think I can draw on here. Let's try it. I want to draw. Back to here. There we go. So the Boolean expression is, change color, I think, here to black. A, B equals Y. Now it looks like a multiply, but it's not. It's just A and B equals Y. So that's what we call a Boolean expression. For the OR gate, it's like switches in parallel once again. Of course, the 0 up here indicating, let's get a little bit smaller pen here. Size smaller, okay, it's better. The 0 here indicating the switch is open. A little bit more ink there. Maybe there. A pen. There we go. Weird. Okay, what's going on? Anyways, the 0. There we go. Now it's really thick. Fun with technology. The one being that we're going to pass voltage. So the expression for that guy is A or B equals Y. And I know that looks like a plus. In a lot of cases when you're little, maybe the teacher said A and B equals Y. In this case, no. It's a plus is not an and. It's an or instruction when it comes to Boolean. There's our not. And once again, it's like the switch bypasses the light, so this will be a lower resistance. Electricity will, most of the current will go that way and the light will go out. Maybe not 100% out, but it will be dim. And of course, our expression was A equals A naught, or A bar. Ouch. The NAND gate, once again, notice how they've got the inverter gate on the output. Oh, I see. I can't draw. I can't not draw in the picture. So yeah, so the picture is not down here. Okay. And then you'll notice the expression. So the original AND instruction was Y equals AB, and they do tend to put the Y on first, or sometimes they'll put them on. It doesn't really matter. It's just like 4 equals 2 plus 2 is the same as 2 plus 2 equals 4. But you'll notice here, because of the inverter gate, the Y is negated, but rather than putting the bar over the Y like they did with inverter gate, they put the bar over the whole equation, which is down here. So that's the equation for the NAND, the Boolean expression, I should say. It looks like an equation. And it's like having the inverter gate on the output of a regular AND. But when we draw the symbol like this, that little circle indicates we have an inverter gate. NOR, same idea. It's like an OR. There's our little circle. That's indicating our inverter gate. It's like an OR with an inverter gate on the out. Now a regular OR was A plus B. And because of the inverter gate, we don't put the bar over the Y, we put it over the whole equation. So that's important to get your head around because it comes back to haunt you when we look at flip-flops and some other things like just some logic in general as far as LEDs and stuff go. And there's the symbol for the exclusive OR, and I'll see if I can get that truth table in here without being too messy. Make it black, make our line a little bit narrower here. And our, well, let me draw on here. No, where is my pictures area? Not going to let me do it. So we'll have to, it's exactly like an OR, except for the last output is not true or not high. Get it on there. Nope, I can't. That's strange. Let me do it there. Oh, here we go. No, I'm at the edge of the drawing, so that's part of it. So I'll see if I can, it's on the, I think the worksheet, so it should be okay. But basically, the output would be 0 for 2 inputs, 0, and any one input would be a high output. 2 high inputs would mean a low output. It's like a three-way switch. Here's our gates again, and or not, NOR, and an inverter gate, which is also called a NOT, and the European equivalents. Now you'll see these in PLC type logic as well. As far as those symbols go, we can use those as blocks within inside a PLC. But they're once again equivalent to switches in series and parallel and stuff like that. The timing diagram. So you'll notice here when both of these go high, so does Y go high. And if B happens to go low, reset. Yeah, so if A goes high, B goes high, so does Y. But as soon as B goes low, so does Y, and it doesn't come back up again until both A and B go high. And you can see what they call a timing diagram indicating the state of the output of Y. So if that was a light on the output, it would be on here, then off, then on, then on. Timing diagram for NOR. Sometimes it's easy just to follow. If we're looking at what happens to a NOR, normally right now we've got ones or zeros, I should say, would make the output true, right? So in order for a NOR to have an output true, both A and B, or B, I should say, have to be 0. And we can see that this goes 1. So any high makes our Y go low. So instead of a 1 making a 1 makes a 0. So it's the opposite of an OR. Head hurting yet? Makes my head hurt sometimes. Okay, learning task 3. This is basically a review again for the Boolean expression, or what they call Boolean algebra. Now they'll write this instruction as, let me write on here, that's too small. The picture itself is too small, so I'll see if maybe I can do this on a PowerPoint, would be better. Unless I got room over here. No, it doesn't look like it. Well, maybe here. Okay. So A or B equals Y. A lot of cases written y equals A or B. And when you write the expression for a combination of gates, which can happen, we can use a combination of gates. In this case, they talk about grouping the equation together, kind of like math. So on the bottom here, I'm hoping that this will write. Oh, let me write. There we go. The AND instruction here has its own little equation. Where's my range of view here? Okay, so that has an A, B. That would be written in brackets. So the equation actually ends up being A, or indicated by the plus sign, A, B equals Y. So that gets a little funky. Now, I don't know why they have an A over here. That just doesn't make sense to me. But they show the equation. Oh, they do show an A. Well, they did mark it A when Y equals A. So either way, usually it's a Y on the output. But just that having that the A and B in brackets indicates that that is the expression for this AND instruction, and the plus between the two indicates that we have an OR combination as well. So here we're looking at a 2-input or 4-input. We got 2 ORs feeding an AND, right? So the book, they got A, B, C, D. That's okay. So what you could write it like A or B, and you can put it in brackets. C or D equals Y. So these brackets indicate the OR instruction with a plus in between. And of course, the very last thing is an AND. So that's why, and sometimes I'll put a dot in between to give you an idea what that combination is. Now, I know the book does something a little funky with W's and stuff, but try and keep it simple. The results end up being the same. Here's our, I think, our W's. Yeah, so W equals A plus B, or A or B, and W2 equals C or D, and then they go Y equals W1 and W2. So that's just another day a way of writing it, but then they show you the actual equation as AB is 1, W1, I believe. I think I got room here. Yeah. A or B is W1, and C or D is W2 equals Y. Now, when you look at that equation and what is the equivalent of switches, the switches for me make a whole lot more sense. If you think of our original OR instruction as having like 2 switches in parallel, so basically we have 4 switches total, 2 switches in parallel here, 2 switches in parallel here, but in series to satisfy the AND. So they do show that here. So this is one OR. A or B. This is the other, C or D, and there's your AND, right? The dot or just brackets, right? So if we rewrote this with brackets, you would not see anything. You just smush it together. And here we just have a coil controlling a contact, making our output go high. So we could make A true, but we'd need D true, or C true in order to turn our light on. Now we could go these both closed and our light still isn't on because we didn't energize our coil. We need to energize that coil to close that contact. But if we do this one, it will turn on, or if we do this one, it will turn on. And the same would be true for the combination here. We could have just one on, but both of these, either that one or that one would be on to satisfy our output. So sometimes it makes a little more sense to just look at it as switches, just to get it straight in your head. Now 3 input OR, you could write it like that, but I would prefer just using what they put in there. 3 input OR would be well, they're just developing the expression for that top one. So you could use W1, W2, W3, but does that make sense? So start by letting A and B equal W1, C and D equal W2, and E and F equal W3. Yeah, sure what they're going there. 3 input OR, I would just go like this. A or B or C equals Y. And that would be a 3 input OR gate. I guess they're just showing the different combinations. Either way works. Next one, they're just doing something the same again, but in this case we've got an A and B for the AND, a C and D, and an E and an F, and that's all indicated by brackets. So we've got ANDs. By the brackets, the dot in between means they're ANDs, or they can just write them straight up. The plus in between means we're feeding an OR. Of course, the W1 through 3 here is just representing each of the AND combinations. But that you could write that expression. You'd probably see this most likely a more common way of doing it because of the way this is labeled on the input than using the W's. Here they're showing the ladder diagram of the equivalent. So A and B, there's one of our ANDs. There's another AND and another. So either one or either this and this has to turn the light on, or this and this. So the series portion is the AND the parallel portion is the OR. Okay, so they also get into some of the laws of Boolean algebra, idempotent rules, the laws of complementation, De Morgan's laws, cumulative law, distribution laws, associated laws, and laws of absorption. So they're very similar to just plain old math. Do you have to memorize them? No. But we are going to look at De Morgan's in a little more detail, or De Morganizing laws. So basically, what we got here, this is what we call a NAND. There's our Boolean expression. Right, if I can circle that. If we want to demorganize, there's some simple rules. We basically change the sign and then negate the inputs and the outputs. So what does that look like? So here we changed our and. Before we had, let me draw here. No, okay. So before we had an and, what did we do? We changed the sign, and then we negated the ins. We changed this from an and to an or, and then negated the in and the out. Well, two negatives make a positive. So you'll notice where the bar is now, it's not over the whole equation. It's only over the bar is only over the input in this case, because the output is not inverted. Now, if the output was inverted, then the bar would go over top the whole equation, as we'll see later on. So that's the demorganized equivalent of an AND. So it will have the exact same truth table as an AND. Oops, and of course, the drawing here is incomplete. Let's see if I can fix it. Not sure about your drawings, but this one wouldn't work very good. So the two switches in series are the NAND instruction. The normally closed contact is our inverter gate. So if we push A and B together, our output will go out. Right now our output is glowing or on. Now when we look at the opposite, our coil right now is energized, so that means this instruction is true, where our light is on, same as over here. If we break A, our light stays on, just like if we pushed here, our light would stay on. If we pushed B without pushing A, our light would stay on. Here, if we pushed B instead of A, our light would stay on. And in order to turn the light off, we have to push both A and B. So even though it looks like an OR, it is exactly the same as far as the truth table goes as the NAND instruction. So here's a NOR, and notice the bar is across the whole equation, right? Indicating we have an inverted output. So A or B not equals Y is how you would say that. Now we've changed the sign to an AND instruction, and we've negated the input. So this here was a 0 before, we've made it the opposite, and now it's a 1. And the same as B, but where this was a 1 before, now we've negated it, and 2 1s make it 0. So we have no output there. But you notice how the bar now is over the inputs. So this truth table would be the exact same as a NOR. What would you call that? Two negated input AND gate. It doesn't really have a name. So if we looked at this 3 input AND gate, so there's our A and B and C. It's not really a multiply. It's just that's the way it's said. You don't have to put the dots. So in order to demorganize this, we change this here to an OR instruction. So we change that, and then we'd negate all the inputs and the output, which they did in the next picture. Now the equation is very interesting. You'll see that the bar over the A is representing this dot, the bar over the B, and so on, right? The bar over the whole equation is represented by the bar indicated there, negated output. So not A or not B or not C equals why not? Funny. Who thought of this stuff, right? So demorganize this instruction. So we've got A naught or not A or not B equals Y. We change it to a AND instruction, and we've negated two negatives make a, two ones over there would make the opposite, a 0 here and a 0 here. And we had on the previous one nothing, so by negating it we turn it into a 0, which means that there's a 1 there. And of course our equation now is A and B not, indicated by the bar over the whole equation. So this isn't really a specific instruction per se. It looks like an AND gate or a NAND, but we also have an inverter gate on the input. So that's the little bar there. That tells you that's an inverter gate on the input. The ABC is telling us that it's an AND instruction. Now the output negated is represented by the bar over the whole equation. So in order to demorganize or make this the equivalent gate, we would change the sign to an OR and negate the ins and the outs. So if there's already a 1 here, it would make it a 0. If there is a 0 here, it would make it a 1. And you can see that's what they did. And the equation changes. So now the bar over top, the B, is indicated by this inverter gate, and so on, right? Where we have nothing for the A, and the output is still the opposite, so no bar over the whole equation. Another example, 4-input NAND and the demorganized equivalent. Basically inverted all the inputs, and because this one's already inverted, two inverts make a normal. Of course, the sign was changed to an OR, right, as you can see over there. Kind of simple to do, just have to get your head wrapped around it. Okay, then it gets into encoding and decoding. And these are a little bit of fun. Try and think binary. I know you just got binary introduced to you today. But here we have A, B, C, and D. And all these switches over here are doing something. And the easiest way to follow this through, if I can draw on this, yes I can. I'll make this a little bit smaller. Smaller size, maybe it'll be better there. Color, red usually works pretty good. So you'll notice here we've got 5 volts. So up here, 5 volts. So right now, this switch is passing power. So you can write a 1 in there, and that's what I like to do. And also, this switch here is passing power. So there's a 1 in there. Now this is where you got to think about that instruction is a NAND, indicated by the little dot on the output, right? The little circle. So when we have 2 highs on a NAND, that means this output here would be 0, right? And based on the diode direction, right, we got to think of electrons flow in this direction. You can think of conventional flow and go the other way if you like. It's really up to you. But based on the bias of the diode, that light would be off. Now 7, if we turn 7 off, that means there's going to be, we got a ground there, it's a low, so that means this will be a 0. All the rest will be 1s. You follow them back through. And because 1 is a 0, that means this output will be a 1. Right? Before we needed all, so this is a 4-input NAND. We need all high inputs to make that a 0. So if any one of these inputs are a 1, or I should say a 0, we're going to have a 1 output, which means our light's going to be on. Same as down here. You can follow 7 through. That means there's a 0 here. Following it down to A, that means there's a 0 here. So that means all of these are going to have a 1 output indicated here, meaning that those 3 LEDs are on. Now, if you looked at this as a binary counting, with A being the least significant digit, you can hopefully make a little more sense of it. Looking at A, B, C, D, 1, 2, 4, 8. So we have 3 1s on, right? We can see those 3 1s. We have the count of 7. Now, if 7 was made and we pushed 8, then just this one would light up. If we push 9, when you follow it through, and it's a good exercise to get used to it, let's just follow through 9. Let's say that 7 is here. Thinking of this as your least significant digit, this being 1, 2, 4, 8, you'd expect when you push button 9 down here that this would come. We need a 0 there. We need to turn this output to a 0. We need a 0 there to, well, we need a 1 on, I should say, to turn that on. And a 1 down there. That would give us a count of 9. So by putting this low, that means we have a 0 here. That means our output goes high. And there's a NAND. Any 0 on the input will give us an output of 1. And then when we follow that down to the very bottom, there's no dot there, so it doesn't connect. That would mean this was a 0. All the rest are going to have 1s on them. But this one here has a 0, so that means this would be on. So it takes a little practice, but and maybe eraser, but you can draw that and follow that through and see that in a lot of cases we are just counting in binary. So that was a decimal to BCD encoder. So binary coded decimal. We'll never go farther than 9 in one digit of a decimal type number. Here is another one. Now, hopefully your module is updated. I think there's an error in my book, but just looking at these numbers here, 0 through 3, this should be your least significant digit right here. So 0 would be your least significant. So right now with zeros here, and this is a neat little exercise to try, that means there's a 0 here. And that's an inverter gate, so that means you have a 1 on the output. Now remember, a 1 is voltage. So following that 1 through, that means there's a 1 there. And where else? That's it so far. Oh, and a 1 here. And following this one through, this one's going to have a 1. And then this one's going to have a 1. Oh, I can't quite get it in there. There we go. So 2 1s here means this light's going to come on. Right? So just with no inputs, our 0 light's on. So that's a count of 0. So the trick is which is our least significant digit? Is it A in this case, or is it B? So let's try A first. Let's say we put a 1 in A. That means this is going to turn to a 0. So that means this is a 0. So A can't be the least significant digit. B is. But let's just follow it through. So 1 is going to come down this way. This is going to be a 1. And this is going to make this a 1, which is this is a 1. And with a 0 here, that means there's a 0 here, so that's not a 3 count. That means there's a 0 here, which makes this a 1, which makes this a 1, which turns light number 2 on. So in this case, A is not the least significant digit, B is. So that would mean, if let's see if I can do a truth table in here, B, A. So if I put a 1 in B, it should turn, being a least significant digit, it should turn on light number 1. And a 1 here would make this a 0. Also, we'll make a 1 here, follow it through. A 0 here on A makes this a 1, which makes this a 1, which turns on our light 1. So that is true. So a 0, 1 would make light number 1 come on. And put that B back in there. If we put a 1 on A, we already seen that it's going to turn on light number 2. What happens when we turn on both? Put a 1 here, which is meaning voltage. 1, 1 means 0, 0. That means a 0 here, a 0 here, so we can't be 0. Also means a 0 here, so it can't be 1. And a 0 here. Now we do have a 1 here on this one, but we need 2 1s on an AND to make it turn on. In this case, we have a 1 here and a 1 here. Our light number 3 will come on. So in this case, B was the least significant digit. If you think counting in binary, you can do all the combinations. And it's good practice to use that just to get all your combinations. Now this one looks scary. Half the battle is understanding what's going on. Why is light 7 on when we have A, B, C, A through B, C on? Now, I know they've written it this way, but in this case, A is our LDS, least significant digit, and D would be our most significant digit. So literally, if you think of binary counting, 1, 2, 4, 8, and of course with a 1 in each of those digits, that adds up to 7. Now the trick of following this through is we'll notice here that, let's just look at number 8. With a 0 here, we have a 1 here. With a 1 on the input to this inverter gate, that means this will be a 0. So anything connected to that would be a 0. So remember we need all 1s to make the output of this a 0. In this case, this is something called syncing. We are actually supplying a path to ground by turning this to a 0. So in this case, this would stay a 1 because we have a 0 there. We need 3 1s to turn that off. Now, on this, or 4 1s, I should say. So for the 7, we're looking to make this a 0. In order to make that a 0, all 3 of those have to be off, or 4 of them. So let's follow it through. This A comes along, makes that a 0. So that means this is a 0. This guy here So actually all these have to be a 1 in order for this light to turn on. So we need at least a 0 in each one of those, I believe. And so if we look at this 1 up on A, makes this a 0, which makes this a 0, a 0. So that is a 1, so no voltage passes. Also here, that makes this a 0. So that means that's a 1, so no voltage passes. And of course we follow A all the way over to 7. Is it even attached to 7? No, it's not even attached to 7. This portion is. So because this is 0, that means this is a 1. And that means we'll have a 1 here. Following that correctly. And yeah, because we need to turn that off. Because these ones are on, we have to supply a 0 here. So in order to do that, we need all 4 of those at 1. So now we have a 1 on here in B, which makes this a 0, which makes this a 1. Following that through, are we connected to 7? Yes, so we have a 1 here as well. And then the C, if we have a 1 there, that makes this a 0, which makes this a 1. It is also attached here. Right, and of course with a 0 on our 8, that means this is a 1, which is also attached to here, which means this goes to a 0 and allows our power to flow through the light. With 2 voltages, there's no potential difference, no current flow, no path to power. So this is what we call syncing. This is going to come back in process control. Syncing switches a path to ground. So it's like switching the neutral or switching the negative side in this case. Where sourcing is would be switching the other way. We would need to have a 1 there to turn it on. But the key point is here is the voltage. In order for a 1 to turn that on, then this would have to be a ground instead of a source. So that's a little messy. If you didn't see that point, it's but that's what I'm here for, to point those little details, and hopefully you can wrap your head around it. So that's the end of learning task 3. So yeah, so work your way through those best you can. We'll cover some more tomorrow and go through the worksheets, of course. So I'll stop it there. Anything else I wanted to say? Oh yeah, the worksheets. Good to do those along with that and hopefully get your head wrapped around it. Worksheets are, you'll see now they have, the answers are open. So now you have, let's see, up to learning task 3. So don't worry about 4, 1 to 3. They give you some examples and Boolean expressions, how to demorganize, and of course what to do. Try it out, see how you make out. And it takes a little bit of practice. I know it always messed me up when I went to school, but it always happens when we see something new. But the worksheet answers are there as well. So try it out, see what happens, and of course send me a note, have something ready for tomorrow. Any questions, and we can hash it out. Okay, for now, I'll stop.